recall something that we said before. Suppose we know f of x. No. Suppose we know that f prime of x is x. Okay. What can we deduce about f and how? Suppose you know that f prime of x is x. What can you figure out about f itself? I actually want you to think about it for just half a minute. No, I don't want you to think about it. I want you to talk to somebody for half a minute. Talk to somebody next to you. What can you say, and how do you know that? What can you say about it, and how do you know that you can say it?
I think if you use that version, the f is x squared. So it's like when you take the derivative of
Okay, so who would like to say something about it? Who would like to say something about it? Maybe Stefano, you actually had your hand up way earlier than everybody. What would you? What can you say?
This is an antiderivative. Instead of multiplying by the degree and then subtracting 1 from the degree, you add 1 to the degree and then divide by that degree.
Okay, so you're saying
So it's
f
squared over
is x squared over 2?
I think so.
Is that what you're saying? F of x is definitely going to be x squared over 2. Is that what you can say about it? So maybe. Other people have things to say? It has to be x squared over 2?
Well, x squared over 2 plus a constant because the derivative of the constant is 0. So
okay, it could be. So Stefano's observation, I think, is that it could be x squared over 2, right? Because when you differentiate this, certainly the derivative of x squared over 2 is 2x to the 1 over 2 times x. Right? So it could be x squared over 2, and Victor is saying, well, it could also be x squared over 2 plus any constant. So any constant c, right? Because again, certainly the derivative of x squared over 2 plus some constant is going to be x plus 0. Right? So it could be these things, right? Can anyone say a little bit more? Could it be anything else? Could it be anything else? Stefan?
The area under the graph.
The area under what graph?
Under the graph of the.
No, what I mean is, could it be some other function? Is there some other function that might work?
I don't know. I don't think so.
No function.
No other function. Why, Mariah?
Because you told us
Because I told you
week or
so.
two ago.
Wait, say it. I'm sorry.
You told us a week or two ago that there's only one.
Yeah, there's only so it can't be anything else. In fact, it's not just that it can be these things, but these are the only things that it could be, right? It can't be anything else. Can't be anything else. Why not? This is really the key, right? This is really the key point here. Okay, why does it have to be something like this? Does anyone know what this is what tool we're going to rely on? Claire.
I don't think this is the right tool.
Okay.
But my reasoning was that when you take the derivative,
Yeah.
you subtract 1 from the exponent.
Yeah.
So when you take the the antiderivative, or like what f is, you
Mhm.
add 1 to the exponent,
Okay.
and you can only get one number if you add 1 to it.
Okay, so it's certainly true that when you take the derivative of a polynomial, right? When you take the derivative of a polynomial, then you take 1 off of the exponent. You multiply it by the exponent and take 1 off of the exponent. Yeah. So, but what if there's some other strange function that we haven't met yet? How do we know that there's nobody else? Certainly, if you say I know that f is a polynomial, then I'm sort of like, okay, I give up. That's the only thing. But there's something you have to say here. Why this is the only thing? Does anyone know what theorem I'm looking for? Kiban.
Is it the mean value?
It is the mean value.
Oh my gosh, I was going
I'm
to say
good
that as a
at
I was
gonna
like,
guess
would be
that.
funny.
Okay, wait. So why is it the mean value? Why?
It looks like, it's like, I don't remember the exact way, it's like f of x plus c equals g of x. If q constants have this, or if q functions have the same slope, or like.
Same derivative. That's
Same
right.
derivative.
That's right. The same slopes, same instantaneous slopes. Good. I'll give you a point for that on final if you want. Okay. Yeah. So why not? The point is the mean value theorem, right? The point is that recall that the mean value theorem says one consequence of the mean value theorem was that if two functions, let's say g and h, if g and h have the same derivatives everywhere, then g must be h plus a constant.
Could it be vice versa? Could it be vice versa?
Certainly, vice versa is true, right? If two functions differ by if two differentiable functions differ by a constant, then they're going to be they'll have the same derivatives everywhere. Yeah. So So the mean value theorem makes that a two-way statement. This way is immediate, right? But the mean value theorem gives it the opposite direction. Right. I'm gonna just put this. Okay, and so you put those things together, right? So you know that f prime x is x. You know that the derivative of x squared over 2 is x, right? Right. So you also know that the derivative you guessed this function x squared over 2 is also its derivative is also x, right? And so what does that tell you? That whatever f is, it must be it has the same derivative. F and x squared over 2 have the same derivative, and so they must differ by a constant, right? So f must be x squared over 2 plus some constant. Okay. It has to be. There's nobody else that works, right? You can search your whole life for somebody else. You're never going to find it. Okay. It's like it's soulmate or something, right? Okay. Okay. So I hope this is clear. What the difference is, right? Saying this sort of thing, it is more like these things work, right? These things certainly have a derivative of x, but it's the mean value theorem that tells you that that the only things that have a derivative of x have to be of this form. Okay. So that's the key point. So okay. So this brings us to the definition. So let's say let I be an open interval. If f prime equals little f on I, we say capital F is an antiderivative of little f on I. Okay, so for example, what we just said, x squared over 2 is an antiderivative of x, right, on the real lines. And what we're actually noticing is that if you find one antiderivative, then you found all the antiderivatives, right? In fact, x squared over 2 plus c, right? I should say, in fact, the collection x squared over 2 plus c, where c can be any constant, is all antiderivatives of x on R. Because of the mean value theorem. Yeah, Claire.
In fact, the what?
The collection, sorry.
Okay.
Yeah, I think it's sort of cool to use an X. Maybe it's not that cool. If you look at old books from like the late 19th century, they actually spell collection with an X rather than a collection. Okay. So there's some notation. It's sort of a pain. It's sort of a pain to say to write this sort of thing. This set x squared plus c, where c is in R, is the set of all antiderivatives of some function. So there's a simpler notation. One writes when we write something like this big S f of x dx is used to denote the collection of all antiderivatives of x. And it's called the indefinite integral. Okay, so for example, instead of writing this long statement out here, right? When usually it's like this. Right. So you write this, right? The collection of all antiderivatives of x is x squared over 2 plus c. Okay. That's instead of writing this collection. The collection of x squared over 2 plus c, where c can be any constant, is the set of all antiderivatives of this function. So it's just a faster way of writing this. Okay. Is everyone okay with this? Okay, so this thing is called the indefinite integral. There's something else called the definite integral. Okay, so the indefinite integral is just the collection of all antiderivatives. Okay, the definite integral is actually related to area, right? So later on we'll see this thing called the definite integral, and it uses a very similar notation, except you put sort of boundaries on it. And what that stands for is basically, it's not exactly right, but it's basically the area under the graph of the function between over the interval AB. Okay, so that thing's called the definite integral. But you see, it's seems to be something quite different from the indefinite integral. But the miraculous thing that will happen is that those two things will be linked together via the so-called fundamental theorem of calculus. So, which maybe it is the greatest theorem in calculus. Okay. So for example, if I write something like this, right? What does that mean? That means the set of all antiderivatives of e to the x, right? So what's the set of all? What is that?
Cx plus c.
E to the x plus c, right? No, the e to the x plus c, right? Because you know that e to the x is one antiderivative, because you know e to the x is an antiderivative, and the Indefinite theorem tells you that all others must be of the form e to the x plus some constant, right? So when you write something like this, it means that these are all the antiderivatives. Right? If I write something like secant squared x, what's the collection of antiderivatives of secant squared? Does anyone know? Tangent, yeah. So tan is 1, and then you add on all possible constants. You could be kind of silly about this, and you could say the antiderivative of e to the x is e to the x plus 1 plus c. Right? That's actually a perfectly legitimate answer. Right? It's just dumb. Right? Because adding on this, so you'd say, well, look, e to the x plus 1 is an antiderivative, right? And so all the other antiderivatives have to differ from it by some constant, right? But really, I'm just creating the same set of functions anyway, right? Because I might as well, absorb the 1 into the constant, right? That 1 is a constant anyway. I'm not really changing the set, right? Okay, so but I hope you see that these are the same answer. Is that clear? That these are the same answer. Okay. Right. So you could that's a perfectly legitimate if sort of inefficient answer. Okay. Here's another one. What about if I say something like this: 7x to the 3 halves minus 4 dx. What's that? What's the collection of antiderivatives? Well, you have to find one antiderivative and then just add on all constants. So take 20 seconds and write down one antiderivative and then write plus c. Okay, turn to somebody next to you and say, this is my antiderivative. Okay, so who would like to, would anybody like to make a guess? Yeah, Madeline.
I got 14 fifths x to the 5 halves.
14 fifths x to the 5 halves minus 4x. Right. And how'd you get that?
So I added 1 to the 3 halves, and then so what would you have to multiply 5 halves by to, and it was 7 as your collection?
Yeah. So you say, well, you say, well, x to the 5 halves, when I differentiate x to the 5 halves, right? I don't know, maybe this is how you might think of it. When I differentiate x to the 5 halves, I get 5 halves x to the 3 halves, right? So that's pretty good, right? I've got the 3 halves, but I'd like to have a 7, right? So I'm going to multiply by 14 fifths on both sides, right? And that will give me the 7x to the 3 halves, right? Maybe that's one way of thinking about it. Okay. So that gives you that the derivative of this is 7x to the 3 halves, and then you also have this minus 4, which is easy. You just have minus 4x. Okay. Same sort of guesswork is involved in something like this. If I say sine 8x is x, well, maybe one way to do it is to make an initial guess. What would be your initial guess? Mercedes? Cosine 8x. So I say, okay, cosine 8x, if I differentiate that, and I'm going to leave space for a constant. If I differentiate that, well, I get negative 8 sine 8x, which is not quite what I want. I actually want just sine, right? So I'm going to divide everything by negative 8. Right? Just multiply both sides by negative 1/8. And so you see that this is an antiderivative of the integrand. Right? So this function is called the integrand. If this is called the indefinite integral, this function here is called the integrand of the integral.
Wouldn't it be negative cosine?
Mm-hmm. So you get negative 1/8 cosine 8x.
Can you explain it again?
Yeah, sure. So, right. So maybe you think, okay, I'm looking for something whose derivative is sine 8x, right? So maybe your first guess is, I'm going to guess cosine 8x, because I know that the derivative of cosine is negative sine, right? But when you differentiate it, you find that you get something that's not quite right. You get negative sine 8x times 8, right, by the chain rule. Right?
Yeah.
Okay, so we've got negative 8 of what we wanted, so you just divide by negative 8 on both sides. Right? Then the derivative of this thing is what we want. Okay? So it's just guess and fix, basically. Okay. So you get negative 1/8 cosine 8x. Let's see. Okay. Couple more. Let's say this one. Sine squared x cosine x. Sine squared x cosine x. So make a guess. Later on, we'll give you a more sort of systematic method than making a guess and then fixing it up. But for now, just make guesses and fix them up. Megan? Oh, do you have the answer or you have a question? You have the answer. Don't tell me the answer. Okay, turn to somebody next to you and say what your answer is. People are shaking their heads. Okay, so the hint is, what what rule of differentiation do we have to understand? Do we have to reverse?
Anti-product rule. No.
Not the product rule,
Sorry.
but the chain rule. Right? So think about the chain rule. Just like here we had, right here we had to understand the power rule. How to use the power rule backwards. Here we're using the chain rule backwards. Okay. How do you reverse the chain rule? Okay. Think for another minute, please.
We use like the power over on the exponent. Just pretend some x is just the power rule can just like I don't know.
Okay. Okay. Talk to somebody next to you if you haven't started already. Right, nobody's talking to you. Talk to Stefan. He's nice.
The derivative just ends up being that negative cosine squared x, you get sine squared x, right? And then you do the inside, and then you just get cosine x.
Oh, okay.
Good, yeah.
And then
Because if you do,
so that's the derivative
it's
of
cosine,
sine of 3.
it's a chain.
Like, like 2.
Versus sine of 3. So
Okay. I'd like to hear some guesses. What do people think?
I think so.
Guesses? Stefano?
Negative cosine squared x
Negative cosine squared x. Other guesses?
plus 8.
Kimaya?
1/3 sine of x.
1/3 what? Sine
Sine of x.
of x cubed, right? Which people often write. People, unfortunately, usually write
Yeah.
like this. Other guesses?
You didn't put a question mark next to that
Okay. As you might guess.
one.
This is it. Right? Right? You think, okay, I want something when you differentiate it, I get a sine squared, right? But it's a little bit tricky, right? This one you really have to understand the chain rule and your differentiation of trig functions, right? So Kimaya makes a good guess. She says, well, 1/3 sine x cubed. If you differentiate that, right? So let me just use the sine x cubed to start off with. Okay. So maybe your initial guess might be sine x cubed. You differentiate it, you get 3 sine squared x times the derivative of the sine as cosine x. Right? That's good. Right. So that's good, but you got 3 of it, so let's just divide both sides by 3, and that gives you 1. Okay. So the answer is 1/3 sine cubed x plus 3. Clay?
Do you have any tips on recognizing that it's the chain rule?
Not really. It's more something that you what happens is that you see something and you see something's derivative, right?
Okay.
You see
Yeah.
something's derivative,
Okay.
right? So you see something to a power. You see something to a power, and you also see its derivative, right? So that basically clues you that
Okay.
this is going to involve a chain. Yeah, go ahead.
I'm confused how you got from how that squared on one side turned into a cubed on the other.
So the derivative, right? So sine x cubed. If you differentiate, are you confused about what I just erased?
Yeah.
Okay, good. Okay, so if you take, what's the derivative of this? 3 sine x squared times the derivative of the inside guy, cosine x. Right?
Yeah.
So that's it. By the chain rule.
Okay, but that's not.
Okay, and remember what we're looking for. We're looking for something whose derivative is x sine squared cosine x. Here we got something whose derivative is 3 sine squared cosine x. So we just divide both sides by 3.
Okay. That makes more sense now. It's still a terrible concept.
A terrible concept.
Yeah.
Yeah,
Whoever
so
invented it.
it'll be more systematic. We'll make it more systematic later. Okay. Okay. So last one for practice. X squared plus 1 to the 100 dx. So what do you say when you see this? What's your first reaction?
Darn it.
No. Chain rule again, right? You see it. Chain rule again. Almost exactly the same problem.
If I don't see like the something and then the derivative.
Look harder.
Yes.
Look harder. It's same. Keep on working, and then we'll talk about each other. Try it yourself first. Give it a good try yourself. Okay, turn to somebody next nearby.
Okay. Go first. Okay. Which one you're gonna?
So does it ask?
Okay. Right. So which one are we gonna do? Yeah. I want to say that I did the whole. Yeah. So yeah. Yeah. So this is the one that you're gonna look at first. Yeah. Okay. So you add one to the calculator. I'm throwing one. Okay. Who would like to say how to do it? Kelly.
X times x squared plus 1 raised to the 101 over 200 plus 6.
Over what?
201.
202. Right? Right. So So again, you say what?
Wait, no X.
No X. Right. Did you say X and I didn't? You didn't say X. Good. Okay. Right. So you say, okay. Well, look. If I differentiate this, right? If I differentiate this, then I'm going to get 101 x squared plus 1 to the 100 times 2x. Right? And you see that that's pretty close to what you're looking for, except you've got this 202 on it. Right? So you just divide everything by 202. Okay, so this guy is an antiderivative. X squared plus 1 to 101 over 202. Yeah.
You can never divide variables, right? You can only divide constants.
If you divide it by a variable, suppose you
Would
divide
that be
it,
the quotient?
then you'd have to use the quotient. Right? That would mess things up a lot. Right? You see, that's the trouble. Right? That's the thing, that multiplying by a constant, how does that affect the derivative? It just puts the constant over there.
Right.
Right? Right? That's all those sort of silly rules we learned at the beginning. The derivative of some constant times the function is just the constant times the derivative of the function. Right?
Yeah.
Constants, if you multiply by a constant, just multiply by a constant over here. But if you divide it by the variable here, you're saying, I'm going to divide by some other function, right? Well, how does that affect the derivative? Well, pretty drastically. Right? Yeah, go ahead.
When you're dividing it by 202, where does that 2x go?
The 2 and the 101 cancel out the 202, right?
Okay.
You've got 202 on top, you've got 202 on the bottom. The x stays still, right? The x doesn't go anywhere. You end up with this, which is the thing whose antiderivative.
Now issue. Okay.
Okay. So let me actually stop there. I'm going to take again feedback. You remember I took feedback early in the term. I'm going to take feedback again. So let's use the rest of the class just to fill out the feedback. Okay? And I'll pass back some homework while you're at it. So yeah, that's basically the end of differential calculus. And next time we'll start talking about integrals, integration.